In this video, we're going to find the mean, which is also called the expected value of a discrete random variable, and the standard deviation of a discrete random variable. So we talked about that a discrete random variable is a variable that lists all the outcomes in a probability experiment. So they kind of take a moment and refer back to the law of large numbers, which we had talked about when we first introduced probability. In particular, we talked about when you toss a coin multiple times, you expect to get heads. And the author of this book actually referred to Carl Pearson, who actually tossed a coin 24,000 times and got 12,012 heads. That's amazing. I mean, we expect that to happen, though. That's the law of large numbers. But the reason I included this information in the notes is I wanted to point out a really interesting thing. And that was this. And here I kind of put it in parentheses, but I'm going to highlight it too, that the theoretical probability, oops, that was interesting. The theoretical probability and the relative frequency get closer and closer together. So theoretical is, of course, the probability that we expect. Half the time we expect to get tails because there's two possible outcomes and one of them is tails. And the relative frequency is what we actually record when we record the data. So we expect those two things to get closer and closer together. Now, the expected value, which is also called the mean, and we'll even use mu to represent it, okay? The expected value of a discrete random variable is to multiply each value of the random variable by its probability and add the products. So as a formula, that means that we're going to do each x for the random variable, each value the random variable takes on, multiply by its respective probability, and then we're going to add those all together. Oops, that was supposed to be a summation symbol. I had a stroke. All right, there we go. I didn't really have a stroke. Okay. So there's the formula we're going to use, and that's going to give us the mean, which is also called the expected value. So that phrase, expected value, what you expect the profit to be, what you expect the outcome to be. When you see that word expect, start thinking mean. They're talking about the mean of a discrete random variable. Okay, so let's look at an example. Men's soccer team plays soccer either 0, 1, or 2 days a week. The probability that they play 0 days a week is 20%. The probability 1 day is 50%. And the probability 2 days is 30%. So it looks like it's 1 day is the most likely. Find the long-term average or the expected value of the number of days per week for the soccer team. Okay, so to do this, I'm going to actually create a probability distribution table. So I'm going to list all the possibilities for X and their relative probabilities. So X could be either 0, 1, or 2. And then for 0, that was a 20% chance. For 1, 50%. And for 2, 30%. I don't know why I'm adding the extra 0 on there, but there you go. Okay, so according to this formula, to find the expected value, we're just going to multiply X times the probability. So I'm going to actually just do that. I'm going to create like another column over here. And I'm going to multiply X times P of X in this column. So 0 times 20% is just 0. 1 times 50% is 0.50. And 2 times 0.3 is 0.60. So when I add that together, I actually get 1.1. So that is the expected value, the mean. So what that says to us is that we expect in the long term, we're expecting that the number of days that the team is going to play is usually 1 day a week. All right. So, but when they're averaging it out over long term, sometimes they do 2 days, sometimes they don't do any days, but most of the time it's 1, and that's the expected value. So the expected value of the soccer team. Wow, it helps if you know how to spell soccer. Soccer team team. Oh, here, actually, I'm not saying that right. The expected value of the number of days per week. Of days per week the soccer team will play is 1.1. Now, we're aware they really aren't going to play 1.1 days, but that's like they used to have an old statistics where they said that the average family wanted 2.5 children. They don't really want 2.5 children, right? They don't want two children and then a half a child. That doesn't make sense. What they're meaning is it's right in between two or three children. Most people want between two or three children. So if we rounded this number, it would make more sense to say on average, they really are playing 1 day a week most frequently. And that's what you would expect. But the 1.1 comes in because we're saying it's not exactly 1 day a week. It's not always 1 day a week. Sometimes they play 2 days a week. And that does affect this average, this long-term average. Okay, so to find the standard deviation, we're going to find the average distance each data value is from the mean, because that's how we find standard deviation. So what we're doing is we're going to take each data value X, these are the random variable values. We're going to subtract the mean, and I'm referring to this expected value that we found above, okay? And then we're going to times it by the probability and take the square root. That's going to give us our standard deviation. So it's a little bit different formula. It is a little reminiscent of the formula we've seen for standard deviation before, but we're timesing it by the probability in these problems rather than dividing by n-1 or n, depending on what we're talking about. So that's the major difference for this. Okay, so let's actually try it in this problem. They were super nice to give us a table, kind of setting this up for us. And we're going to go through and fill it out. And then get your calculators ready because I want you to make sure you get the same numbers I do. This is referring to the problem we saw in the first section, 4.1. We're looking at the number of times the baby crying after midnight in a week. And we were given 0, 1, 2, 3, 4, 5, and then those were the probabilities for each one. Okay, so we're going to find both the mean, the expected value. They asked the expected value or the expected number of times per week newborn's crying wakes up the mother after midnight. And we're going to use this column to help us do that. So we're going to multiply X times the probability, and then we're going to add that together, and that's going to give us the mean. And then this last column is going to help us do the standard deviation. All right, so X times P of X, so 0 times 250, that's going to give, 2 over 50. That's going to give me 2 over 50. 0. Wow. 1 times 11 over 50, that's going to give me 11 over 50. 2 times 23 over 50 is going to give me 46 over 50. 3 times 9 over 50 is 27 over 50. 4 times 4 over 50 is 16 over 50. And then 5 times 1 over 50 is just 5 over 50. All right, so that's multiplying these two first columns together. And I'm just applying the number to the numerator, with the exception of the first one where it's all 0. Okay, so let's go ahead and add these all up. So let's see, 47, 57, 77, 84, 94, 100, 105 over 50. So I'm getting 105 over 50, which when you actually divide that, that ends up being 2.1. So that's the expected value. So that's the expected number of times. 2.1 times we expect the newborn's babies crying to wake up the mother after midnight in a week. All right. Okay, so now let's calculate the standard deviation. So we're going to take each random variable and we're going to subtract this 2.1 because we need that for this last column here. So we're going to do, here, I'm going to zoom in a little just so I can write a little clearer. So we're going to do 0 minus 2.1 squared, and then we're going to times that by 2 over 50. And I'm going to give you what I got. I got 0.1764. Wow, that's so sloppy. 0.1764. I'm just going to go outside the column. Hopefully you guys can see that. All right. The next one, 1 minus 2.1 squared, timesing it by 11 over 50. That one I got 0.2662. And we're just going to keep repeating this. And that one I got 0.0046. 9 over 50, and that one is 0.1458 minus 2.1 squared over 450, and that is 0.2888. And then the last one, 5 minus 2.1 squared times 1 over 50, 0.1682. All right. Okay, so take a second, add those together. And a rounded value, I got a rounded value when you add these together, total. I believe it's rounded, I'm almost positive. 1.05. No, actually, I think it does come out exact. Never mind. All right, so that's that total. So we found the sum, and now we're going to take the square root. So the square root of this, that's going to be our standard deviation. And that is 1.0247. So there's the expected value, and that's how much we expect it to deviate from each other. In other words, it could go up about 1 or down about 1, and that wouldn't be unreasonable data to be looking at. We'd still be looking at the bulk of the data between those values, which makes sense because the bulk of the data is between 1 and 3. So it makes sense from one standard deviation away from the mean. Okay, let's look at another example. Suppose you play a game of chance in which 5 numbers are chosen from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A computer randomly selects 5 numbers from 0 to 9 with replacement. So in other words, a number can pop up more than once according to the computer. So if it picks the number 0, it could pick 0 again later if it really wants to. Okay, so you pay $2 to play and you could win $100,000 if you match all 5 numbers in order. So it's like the lotto. And you'll get your $2 back plus the $100,000. So on the long term, what is the expected profit for playing this game? Okay, having such a big payout, is it enough to play the game? So let's go ahead, and what we need to do is we got to create a probability table here. So to do this, we're going to have to calculate our odds of actually winning. Okay, so to win the game, since the options are 0 through 9, okay, that means you need to guess all 5 numbers. So we have 5 numbers, first, second, third, fourth, fifth, okay? And the first number, guessing it correctly out of those 10 possibilities, because there are 10 since you count 0, would be 1 out of 10. And the same for the second one, it'd be 1 out of 10. And 1 out of 10, because you could repeat a number. So they're always out of 10. And each of these are independent of each other. So we're going to multiply these probabilities together. And that's going to give us the probability that you might guess it correctly. So that's 1 out of 100,000. Or as a decimal, that would be 1, 2, 3, 4 zeros. Okay, so that's the probability of winning. All right. So the probability of losing then is the complement of this. So the probability of losing is 1 minus this, or 99999. All right, so that's the probability of losing. That's very good odds. All right, so let's create a little table from this and then find the expected value. So we're gonna go ahead and we're gonna find x and p of x, and then we're gonna multiply them together. Oops. Okay, so in this game, there's two outcomes. You win or you lose. Okay. So if you win $100,000. So that is the first random variable, 100,000. But if you lose, you're going to lose $2. Okay. So those are the outcomes. Those are the two possible things our random variable can be. $100,000, you win it, or you lose $2. So we're using a negative. Okay, so the probability for winning was 0.00001, and the probability for losing was 99999. Okay, so multiplying these together, this is going to come out to 1. Yeah, because we'll move the decimal 5. Yep, that comes out to 1. All right, and this one, when you multiply those together, that's going to come out to negative 1.99998. All right, so add those together. So that's going to give us, a total of negative 0.99998. So here's what that means. In dollars, if we're rounding it because we're talking about money, this would round to -1. So that means we're expecting on average to lose $1. That's what that means. If you keep playing this game like over and over again, which a lot of people do with the lotto, right? They buy a ton of tickets and then maybe at some point they finally win. It kind of ends up still working against you. Okay. Often they keep playing after the fact. So this is what's going to happen if you play this game long term, multiple times over and over again. The odds are not in your favor. It's kind of designed so that you're going to lose money in this scenario. Even if you might win, you still might end up losing money in this scenario if you tend or possibly keep playing this game. All right. So let's look at another example. And by the way, most games are set up that way against you. Let's toss a fair 6-sided die twice. Let x equal the number of faces that show an even number. All right, so we are given or asked to find the mean and the standard deviation, and they were gracious enough to show us all 36 possible outcomes. Okay, 36 possible outcomes there. So here's what we're looking at. The number of faces that show an even number. So if you roll the die and maybe you get a 2 and a 3, then only one face shows an even number, right? Or maybe you get a 3 and a 3, then none of them have an even number. Or you get 2 and a 2, and they both have an even number. So really, those are the only possibilities. And in fact, I went ahead and included that in the table down here. So 0, 1, and 2 were the possibilities. And counting up all of them that have 0, there are 9 of them out of the 36. 18 out of 36 have 1, and another 9 out of 36 have 2. Okay, so we're going to use that to help us calculate the rest, the mean and the standard deviation. So let's get to multiplying. So 0 times 1/4 is 0. I got to love that one. 1 times 1/2 is 1/2. And 2 times 1/4 is 1/2 also, because it's 2/4, which is 1/2. All right, so adding that together, that's going to give me a total of 1. And that's the mean in this case. So we're saying the long-term average is that you're going to see one of the die have an even number. You expect to see one of the die have an even number showing? All right. Let's go ahead and use that to calculate the standard deviation. So we're going to take each x and subtract the mean, square it, and times it by that standard deviation. So that's going to come out to 1 times 1/4, which is just here. I'm going to write it in decimal form, 0.25. Here we're going to get 1 minus 1, which is 0. So this comes out to 0. And this one we get 2 minus 1, which is 1, times 1/2 is just 1/2, which is, oh, yeah, no, I did that right. 0.5. Okay. So that means then that when we want to find the square root of this, so we're going to find the square root of 0.75. And I am getting, oops, 0.866. So that is then 0.866. I'll just round it to 3 decimal places.